Ladies and gentlemen, welcome to the first lecture on the second module for the course on ocean structures and materials under the basis of NPTEL IIT Madras. I hope you have followed the lectures on the first module. In this set of series of lectures in second module, we will look the following topics. We will speak about brief outline of planning of ocean structures. We will talk about brief introduction to design of ocean structures. We will also speak about towing, launching and installation of offshore structures and pipelines in this lecture schedule. We will talk about regulations and code of practices involved in construction and design of offshore structures. We will speak about different kinds of foundation systems for ocean structures. We will also speak about seabed anchors, dredging methods and equipments in this module. For benefit of the viewers, let us also look into the outline of the module 1 which we have completed so far. We discussed about different types of ocean structures in module 1. We learnt about various structural systems that are generally deployed for shallow water, medium, deep and ultra deep waters in sea. We speak about various environmental loads acting on offshore structures. We understood structural action exercised by different ocean structures. We also studied different types of coastal structures in detail in the last module. In the present module, in this lecture 1 of module 2, we will speak about introduction, planning and guidelines of offshore structures. Ladies and gentlemen, offshore oil industry has a very old history since the Second World War. In Gulf of Mexico, offshore structures were placed in position in 1945 in just at 6-meter water depth by drilling an exploration well, followed by which in 1976 the first offshore structure of 200-meter depth was installed in offshore California and 300-meter structure was installed in 1978 in Gulf of Mexico. The planning of offshore structures is actually a complex procedure. The main reason is because of variety of parameters involved in deciding the type of structure to be constructed. Apart from the water depth and sea state suitability, functional aspects, geometric form, construction and installation methods keep the selection of structures as a very complex policy in deep sea systems. If you look at the different sea states generally where these structures are deployed, the figure what you see in the screen will show you different kinds of sea states where they are generally deployed. This is the typical curve which shows the northern North Sea states. The x axis of the curve plots different wave periods in seconds varying from 4.54 to that of 100, whereas the wave speed density or wave spectral density is varied in the y axis from 0 to 80. If you look at the wave frequency, which is again plotted on the same figure, the wave frequencies vary from 0 to 1.5 radians per second, while the wave periods vary as a reverse of this in this order. Now, the design state of significant wave heights 15 meters and about T naught 15 seconds, which is the TZ 0 crossing wave period, lies somewhere around here in this region, for which the spectral has been shown. Whereas, if you look at the sea state where the summer storm generally occur in Gulf northern sea states, which has got HS and TZ as 7.5 meters and 11 seconds, you have the curve which is plotted here as it is, and of course, the operational sea state in northern sea which has HS as 4 meter and TZ at 8 seconds looks like this on the same scale. So, there are different sea states varying from 15 meter 15 seconds, 7.5 meter 11 seconds, 4 meter 8 seconds in northern North Sea states, which has been shown here. So, generally offshore structures are planned to deploy in different sea states as seen in the figure, where the spectral density varies drastically with respect to one sea state with that of the other. Alternatively, if you look at the type of platform which is to be installed in this C states, then the fundamental period of complaint type platforms vary from 40 to 60 seconds, which has been shown in the wave frequency here at a lower frequency, whereas the fundamental period of deep water fixed platforms, which vary generally from 3 to 5 seconds, has been shown in this range here. Now, if you look at the input spectrum for which the structures are designed, the input spectrum is again superimposed on the same region where the fundamental periods of complaint structure and deep water platforms or fixed type platforms has been shown. Now, on the other hand, alternatively in the y axis, if you see, the wave energy or the concentration of wave energy is on the y axis, where the complaint structures have been installed or the region where the periods of complaint structures are focused, the wave energy is higher compared to that of the fixed platforms where the wave energy is relatively lower. Now, to understand different planning guidelines which are referred to that of deep water systems, one must realize deep water riser systems which are important in my discussions here. There is a correction here, 1 minute. Deep water. So, let us look at different deep water riser systems as we are now going to discuss. Let us quickly see what are the different kinds of material, types and planning layouts which are connected to deep water riser systems. The deep water riser system, as you see in this figure, varies from different kinds of platforms as you see here. Ladies and gentlemen, depending upon the basis of understanding in lecture number 5 and 6 in module 1, you will be able to name at least few of these platforms which has been shown here. Let us fundamentally ask a question, what do we understand by a riser? Riser actually is a structural member which connects the subsea to the top side. So, the subsea to the top side is a riser. There can be many risers involved, some are meant for drilling, some are meant for production, some are meant for export risers, some of them for injection risers as a process for exploration. There is something called what are the factors driving the design of risers. The floater type, the floater motions, the water depth, the environmental conditions and the design pressure and temperature are important critical factors which essentially drive the design of the risers in deep waters. If you look at the deep water developments in general, there are different kinds of risers which has been provided for different kinds of platforms which is being housed. This is what we call as an FPSO, which is a ship shaped floating system which is also meant for exploratory drilling. You can also link it to platforms like TLPs, TBPs and spars, which are also meant for production and exploration drilling combinedly with that of different kinds of platforms together on the same sea state. So, if you look at deep water developments in general, there are many complexities involved in planning these kind of installations and operations in deep water. To understand them in detail, the foremost question comes, what are the different types of risers which are generally involved in deep water systems? Talk about drilling risers, typically they are top tension risers which is called as TTR in the literature. Production risers are generally flexible risers, steel catenary risers, there can be hybrid riser towers, there can also be single hybrid risers which is otherwise called SLOR, or you can also have grouped SLOR. If you look at the export risers, they are similar to that of production risers, and these are the different types which are generally used for export risers. If you look at the injection risers, they are also similar to type of production risers as flexible, steel catenary, etc. So, there are different kinds of risers, different types that have been generally involved. Essentially the drilling risers are of top tension risers which are unique in nature in comparison to other type of risers which are used for deep water systems. Let us now see quickly what do we understand by top tension risers, briefly associated as TTRs. Essentially top tension risers are provided with surface trees with full well pressure. They have an extensive track record of being successfully deployed in various operational platforms in Gulf of Mexico. They are recommended to be used in a water depth varying from 300 meters to 2500 meters. Now obviously top tension risers, as the name suggests, require a tensioning system which is to be involved or which is to be required to impart tension on the top side of the risers. Now to compensate this, alternatively a mixing string concept of these kind of risers have been introduced in the design stage of top tension risers. Now the photograph what you see here are two typical examples of different kinds of platforms which are employing top tension risers for production drilling. If you look at the pressure involved in drilling risers, if you focus closely on low pressure drilling risers, they are classically used for semi-submersibles, drill ships and jack-up rigs. They generally being used for water depths much more than 3000 meters. Essentially the governing factor for this kind of low pressure drilling risers is that the buoyancy may cost about 50% of the overall riser cost, which makes the riser 98% buoyant. There are three different couplings which has been used in this kind of risers, which are otherwise called as flange, dog and split ring couplings. If you look at a typical cross section of a low pressure drilling riser, the drill string which you see here is at the core, which has got auxiliary strings or auxiliary lines around it, and there are some parallel lines which are otherwise used to kill or choke the well. They are called as kill risers. Generally these risers are about 21 inches in diameter, and there are otherwise auxiliary lines which are subsequently present along the periphery of the core riser, as you see in the figure. If you look at the different kinds of tensioning systems which are generally deployed for top tension risers in production risers of deep water drilling systems, can have air can system or hydro pneumatic tensioning system, which both are commonly deployed in deep water rising systems. If you look at an air can system, spar production risers are essentially fall in this category of tensioning systems. If you look at hydro pneumatic tensioning system, generally they are used also for spar as well as for drill ships and drilling rigs and as well as for TLP. Essentially the tensioning style is mainly used for TLP drilling and production, which is also used for spar drilling, drill ships and drilling rigs. If you look at the ram style, which is one of the hydro pneumatic tensioning system which is used in case of spar drilling risers, it essentially consists of a tensioning joint and the tension ring and the piston rods circumferentially attached to the casing of the tension ring, which is subsequently connected to the hydraulic cylinders at the bottom, which is housed on the cellar deck and which results in a standard joint as you see in the ram style connection of hydro pneumatic tensioning system. Alternatively, TLP is used a tensioning style which is slightly different from that of the ram style, where there is a tree deck on the top which has got hydraulic cylinders placed and mounted in a different angle, which is supported by accumulators parallelly attached to these types of cylinders. They are all connected to a load ring connection, which is then further connected to a TLP production riser. We can also see a drill rig style marine riser tensioner, which is commonly used for drilling rigs and drill ships. You can see here there are different set of sheaves which are connected to the hydraulic cylinders, and then subsequently they are all housed on a load ring where this is further connected to my drilling rig system. In detail, if you look at another type of drilling riser, which is steel catenary riser, which is addressed as SCR in the literature. This is generally connected to that of a TLP, where there is a tapered stress joint which is connected to the top side of the production platform, from where the riser is connected to the drilling units. Now, there are different VIV strakes, because these are the regions where the vortex induced vibration will be severe, and these segments of the riser are subjected and reinforced by streaks which are called VIV streaks in the design itself. The steel catenary riser is essentially consists of a steel pipe, insulated pipe, or a pipe in pipe conceptual system. This is successfully being deployed at a water depth from 500 meters to 2500 meters. They are generally used in TLPs, spars in Gulf of Mexico, and semi-submersibles in Brazil. They can be laid by different kinds of laying system like J and S lay system, or even by a reeling system. Many installation companies do practice installation of steel catenary risers as a very interesting methodology. They have a low material cost, available also in large diameters, and they can sustain high temperature and pressure, and they can be subjected to internal inspection. Pipe in pipe is a very common system of steel catenary riser which has been commonly deployed of late in Gulf of Mexico. They are well known with different kinds of material whose material characteristics and properties are well established in the literature. There are some design challenges related to steel catenary risers. When these kind of risers are attached to large vessels which has got large vessel motions, then they result in large bending at the touchdown point. Ladies and gentlemen, the point where the riser touches my sea floor is called the touchdown point or the touchdown region. Generally, at the touchdown region, it has got subjected to large bending at the touchdown zone, which results in local buckling of the riser. These risers are also unfortunately subjected to high fatigue at the touchdown zone. Therefore, they become the critical failure point of these kind of risers. The soil riser interaction uncertainties causes additional complexity and impose a very serious design challenge to these kind of risers. Therefore, there is something called weight distributed steel catenary riser detail, which is generally done in case of deploying it to overcome the design challenges what you saw in the last slide. This is a typical case where different kind of weight distribution has been occurred along the profile of the riser. The red color what you see here is the normal riser, which comes from the initial point in the top side to that of the touchdown zone on the sea floor. To this riser at different locations, heavy weights like as you see in blue color or light weights as you see in green color are attached to the riser. The design challenges what you saw in the last slide are addressed by varying the weight along the profile length of the riser. The weight distribution is generally carried out by varying the density of coatings or even the steel wall thickness of the riser. The coatings are generally industrially qualified material like PE, PP, PU or rubber coatings, which are generally and commonly used. These coatings and steel wall thickness of the risers vary the weight along the riser length profile, which is otherwise called weight distributed steel catenary risers. These kind of risers, when weight is distributed along the length of the riser, are able to overcome few design challenges as we mentioned in the last slide. The weight distributed steel catenary riser details are generally used in different kinds of platforms. There are something alternative to SCRs which are currently available in the market, which is called flexible risers. Why we are discussing about these kind of risers is that when I talk about design and planning of installation of offshore structures, I must know one of the most important challenge of what are the different kinds of riser material available in the market and what is their adaptability to use them in deep water systems. Let us look at the flexible risers. A flexible riser has got a hybrid combination of different material, as you see in the cross section here. It has got an extensive track record of about 85% of these kind of risers are generally used to sustain dynamic loads. In general, these kind of risers have been started being deployed in deep waters of late, even the depth of 2000 meters. They are also available for large installation vessel fleets in large volumes and numbers. There are only mainly 3 main suppliers available in the world who can prepare these kind of flexible risers. They are very easy to install, they are highly flexible and robust for high dynamics, they have intensive corrosion resistant properties, and they have a very great advantage of reusability. Generally the concept is they have got different pipes which are concentrically connected, as you see in the cross section. These pipe in pipe system are heat treated and developed for a specific use. For example, the inner core what you see here is a carcass material, surrounded by which we have got the hoop stress layer which is surrounding the outer layer of that. The carcass layer is surrounded by the internal fluid pressure which you create around the circumference of this riser. The hoop stress layer which is reinforcing circumferentially the riser or the flexible riser is then covered by a tape to protect this riser from exterior damage. Then followed by this covering, there is an armor layer available in 2 layers which are again further coated and covered by a tape, and which comes with an outer shield. So the entire flexible riser is thoroughly protected, and this becomes completely corrosion resistant and easily reusable. At the same time, they can be used for large installation fleet vessels which are now commonly being deployed at a greater depth more than 2000 meters water depth. There are different kinds of configurations of flexible risers which one must understand before selecting what kind of laying I must use for these kind of risers. The standard flexible riser configuration is also called as SCR, which is used for steel catenary risers, can have a steep wave configuration, can have a lazy wave configuration. The steep wave is a shape given according to the riser configuration as you see in this figure. The lazy wave does not follow a vertical line as you see in the steep wave. This is what we call free hanging configuration. There is no bend in between the profile of the riser. If the riser has a profile bend similar to S, this is otherwise called as steep S, because this configuration initial is comparable to that of a steep wave configuration, and the bent up shape indicates S in its geometry. If this S bent up shape is comparable to that of a lazy wave, then it is called lazy S. We also something called have a lantern shape which is called Chinese lantern riser configuration. The alternate flexible riser configurations, these are all standard riser configurations, can also have alternative flexible riser configurations. Some of them are highly patented and being used in Gulf of Mexico, in US. People have support systems for these risers which is called U shape, fixed S shape, camel S shape, tethered wave shape, tethered S shape, and a lazy camel shape. These are all specific kind of geometric shape of risers which have been used for flexible risers mostly in deep water layouts. If you look at different kinds of flexibles where the steel catenary riser envelopes have been deployed. So there is a figure which shows the riser diameter expressed in inches against the water depth in meters where they have been installed. If you look at, as the riser diameter goes larger and larger, we try to use steel catenary risers for spar, essentially in Gulf of Mexico, where the water depth varies from about 500 meters to around 1700 meters. Whereas till 2002 or starting from 1996, the riser diameters usually restricted to only 18 inches. Now the larger diameter risers have been used essentially when they have got bottom weighted risers, which are seen to be alternate solutions for deep waters. Of course, if one can use low heave benign environment, can use larger diameter for deeper water layouts where the depth of installation can even touch 2000 meters, as you see in this figure. Now alternatively to SCR, we have something called freestanding tower risers, where the risers are generally supported, as you see in the figure here. The first use of this kind of freestanding tower riser has been done in Placid's Gulf of Mexico at a depth of 470 meters from a semi-submersible in Girasol. The tower installation is what you see here in an animated figure. It has got a local fabrication and assembly. This can be recommended for ships and semi-submersibles. The insulation and flow assurance are more comfortable and more supportive for deep water installations. The small subsea footprint and the hang off area are seen to be a great advantage of these kind of risers, because these risers leave only a very small footprint on the sea floor. The vessels, they can load lower than the flexibles in SCRs, they have controlled onshore fabrication, they have low in place stresses because they got tower type supporting system of the risers. They have of course low cost installation vessels to be used for deploying these kind of risers. Generally the different types used for freestanding tower risers are the following. They have got integral, non-integral buoyancy type. They are connected directly to FPSOs and FPS. They use generally lightweight material, therefore the riser configuration and the laying of riser with this kind of support system, the tower support system becomes easy and simple. You can also have freestanding hybrid risers, as you see in this photograph here. They are generally used for deep water applications. They also have a local fabrication assembly which uses this kind of hybrid risers for deep waters. They are very well suitable for drill ships and semi-submersibles. They have insulation and flow assurance characteristics which are highly beneficial for deep water installations. They also leave very small subsea footprint and hang off area, as seen in the figure. The figure what you see here is the riser, and these are all the tower supporting system, and they leave very small footprint on the sea floor compared to other kind of conventional risers. They also have controlled onshore fabrication and low in place stresses, which has been measured by analytical studies by different researchers. It has been also seen they have got low cost installation vessels being required for commissioning these kind of risers in deep waters. They are useful for supporting systems like buoyancy tanks. They are connected to FPS directly and they use generally lightweight material, therefore the installation becomes simple and easy because they have tower supporting systems which are used for installing these kind of risers. You also have something called grouped SLOR risers, where you can see the risers when the tower supporting system are grouped in one, and from there they have been used for different kinds of wells, as you see here further. These kind of group systems are generally recommended for deep water applications. They have a local fabrication assembly which are well suitable for drill ships and semi-submersibles. They also have very low in place stresses, and the low constellation vessels makes this kind of riser installation more economical. In the recent times, people have attempted to use composite production spoolable as a new alternative type of riser. This is a composite material which is being used as a riser material, which is recently being done for depth of about 3000 meters water depth. They can vary, have a diameter from 4 to 16 inches, and they are essentially spoolable. So transporting these kind of risers for installation location on a drill ship or on a barge is simple, because these kind of risers are highly flexible in the form sense. They can be spooled off and they can be transported. The minor track record of these kind of pipelines is one important merit for using these kind of production risers. They are lighter than steel and they are standard flexibles. They have high strength and very good fatigue properties, and the flexibility in composition of stiffness and weight suits these kind of risers for deep water application up to about 3000 meters. There are different types of these kind of risers available. They are flexible risers with composite armor, that is 30% weight reduction happens because of the armor composition in the flexible configuration. New all composite risers are also available using unbonded flexible risers. You also have bonded composites where 2-3 current projects in Gulf of Mexico are being using this kind of composite risers where the weight of the riser is further reduced and make it flexible, so that these risers of even larger diameter can be easily spooled off to be transported from one location to another for installation. If you look at large diameter export risers, because we need to transform or transport the oil or the gaseous connections from the vessel to an offshore facility or from the satellite vessels to the main production facility, we need export risers. Essentially these kind of risers are suspended flow lines. As you see in the figure here, they are usually suspended flow lines. For example, I have a TLP which is having a production riser. I want to transport the crude oil accumulated in this production platform to my barge or my drill ship or my storage facility, where I use this kind of export risers, where essentially these kind of risers are suspended flow lines, as you see in this photograph here. So in this lecture we discussed about different kinds of riser configuration, different kinds of types of material being used for offshore riser configuration, and they will be helpful for planning the layout of these kind of risers in deep water drilling facilities. Thank you.